I think I might have found an explanation for the mysteriously decreasing differential gain at the end of the previous video showing the lab16 differential amplifier after the tail resistor was replaced with a current source. So remember, we showed that the common mode gain had become too small to measure as we intended, but there was a mysterious, it almost appeared that the differential gain had dropped by about a factor of 2. So I think I might have found an explanation for that. So if you look at the data sheet for this transistor array that we're using, the CA3086 transistor array, you see that pin 13 here is marked substrate. And yeah, so if we zoom in a little bit on the photograph, we see that pin 13 is marked substrate, and then we can look at the fine print. And the fine print says, footnote 1, the collector of each transistor in the CA3086 transistor array is isolated from the substrate by an integral diode. The substrate, terminal 13, must be connected to the most negative point in the external circuit to maintain isolation between transistors and to provide normal transistor action. So I neglected to do that in the lab write-up. I neglected to make pin 13 be the most negative point in the circuit. So I think what we should have done is, so using the transistor, pins 9, 10, 11 here is just fine. But this transistor, pins 6, 7, 8, should have been used over here, I think. And then this transistor, pins 12, 13, 14, should have been used down here. So this should not have been 14, this should not have been 12, this should not have been 13. Instead, we should have used 6, 7, 8 here. And this should not have been 6, 7, 8. Instead, we should have used 12, 13, 14 here. And then in the initial stage, when we did not have this current source plugged in yet, I think we should have connected pin 13 to minus 9 volts directly, just while it was unused, so that we prevent those diodes from inadvertently connecting the transistors together. So I think that probably explains why we saw the differential gain drop by a factor of 2. So I've rebuilt this circuit, basically just swapping these two transistors on the 3086 array. So now for the current source, and it's a 0.8 milliamp current source. So this I tail is 0.8 milliamps. I just checked that by measuring the voltage drop across this 1K resistor. And so then we have the collector current through each of these two transistors, and the quiescent state is 0.4 milliamps. And actually another change I just made is I put an identical resistor here as to here, which is a kind of a pedagogical improvement I should have made to the lab in the first place, because then what you see is that this is a negative copy of the output. So it also preserves the symmetry. So it's sort of nice, since we use symmetry to argue for what this circuit is doing, it's nice to preserve that symmetry, at least until you can then remove one of the resistors and show that it doesn't matter if you remove it. So if you leave an identical 10K resistor over here as to here, then pin 8 is the main output, and then pin 11 is an inverted copy of the output. So I'll show you that. And I think I just measured the gains, and now I think they seem more in line with expectations. So here's the I'm set up now to measure the differential gain. Let me show you that. Okay, so you're looking at the scope output now. Let me first show you. So the power supplies are at plus and minus 9 as usual. And then for wave gen, I'm using 2 channels for wave gen. So I'm using them in an identical way. Well, almost identical. So each one, I have 30 millivolt amplitude at 1 kilohertz and a sine wave. One of them is phase 0, the other one's phase 180 degrees, and they are synchronized to each other. Okay, and then I go over to the, so this is a true differential signal then. So I have plus 30 millivolts and minus 30 millivolts. So that is a 60 millivolt amplitude differential signal. It's purely differential. And then I look at the scope traces, and we see, so this is 500 millivolts per division, and I'm using these 2 red cursors to measure. So I'm looking, oh, by the way, the cyan or blue curve is pin 8 here, which is the regular output. And then the magenta or purple curve, channel 3, is pin 11, which is the inverted output. And I have both of these scope channels AC coupled. I could show you in a moment what they look like when they're DC coupled, but AC coupled because there is about a 5-volt offset that I just want to eliminate so that I can change the scale at will and look at the time varying part. And then I kind of there's a little band of noise that it would be nice to get rid of. But I put each cursor kind of in the middle of this corresponding blob. And so this one I said is plus 1.73 volts. This one is minus 1.70 volts. And then I take, I take that difference and divide by 2 because I want the amplitude. And then I divide by the differential amplitude, which is 60 millivolts. And the result is a gain of 28.6. So gain just under 29. 28.6 is what So I take 1.7325 plus 1.6986, divide that by 2 because I just want the amplitude, not the peak to peak. And I divide that by the differential input amplitude, which is 60 millivolts, and I get 28.6. So call that 29 is my differential gain. And the predicted differential gain, which is RC over twice RE plus little re, and remember, we compute little re, that's 25 millivolts divided by the collector current. So, and the collector current is 0.4 milliamps. So that gives us about 62, 63 ohms for little re. I think there's another design flaw in this particular design. I think the quiescent collector current is so low that little re makes a big difference. And remember, little re varies as the collector current changes, so it gives a kind of nonlinear response. And I think that makes it challenging to measure the gain. So I think when I redo the write-up for this lab, first of all, I'm certainly going to swap these two so that this 12, 13, 14 transistor is used for the current source, and when it's not used for the current source, pin 13 is tied to minus 9 volts. But also, I think I want to increase the standing current in a future version of this. And when I do that, I think I have to reduce this resistor a little bit so that the output, the quiescent output value is still within a reasonable range. So I'll wind up trading a little bit of gain for better linearity. But I'm not going to do that now. Okay, so I think our differential gain now makes sense. So we predicted 31. We measured 29. It's pretty good. And then while we're here, let me go to, well, actually, before I do that, okay, so I want to go back and show you the DC coupled versions of the outputs. But before I do that, let me switch to a common mode signal. And let me also give you a quick tour of what is set up here. So, also I'm putting the input signals directly into the two bases here because I became a little bit suspicious of these AC coupled inputs. I became suspicious when I tried, remember in the previous video, I tried to measure the common mode gain. And to get a good measurement of the common mode gain, I had to go directly into the two bases instead of going through this AC coupling network. So I'm doing that now. I'm connecting directly to pins 9 and 6, the two bases. 9 and 7, the two bases. 9 and 6, 9 and 6. Okay. So here's one AWG input. Here's the other AWG input. And then, let's see, pin 6, you see basically here's my input signal jumping over from this capacitor. And then pin 7 is the emitter, so then it goes to this 100 ohm resistor. And from there we jump over to pin 14, which is the collector of this current source, or current sink. And pin 8 is, okay, so for pin 8 we have this 10 kilo ohm collector resistor up to +9. And then pin 9 is the base of the left-hand transistor here. So that goes to this other input block. And then pin 10 is the emitter of that right-hand. Oh yeah, so that has the 100 ohm resistor over to this same area. So I have the 200 ohm resistors coming together. I used to have that tail resistor coming down to -9, but instead I have a little wire to jump over to the current source. And then pin 11 is the inverting output. So let's see, 8, 9, 10, 11. So here is the other collector resistor so that we have an inverting input. So this is another 10K resistor. And then pin 12 is the base of this current source. So we should have 2K to -9 and 10K to ground. So indeed, we have 2K to -9. It goes around this way. And then we have 10K down to ground. And then, okay, and then from pin 13, which is the emitter of that current source, we have 1K to -9. So there's pin 13. We have this 1K resistor, and this is a copy of -9. And then pin 14 is this collector, so that's the current sink. So that's this little blue wire that goes over to where the two emitter resistors meet. Okay, so that's how the circuit is wired up. And I have the two AWG channels. One is a sine wave, one is an inverted copy of that sine wave. So now to do the differential gain, I will just move the AWG2 input over to AWG1. So I have two, oh, you can't see that. I have two copies of AWG1 here. Now I have two copies of AWG1 instead of using AWG1 and 2 separately. And so then, if you look on the waveforms window, we see what looks like nothing. And if I blow this up with a zoomed in voltage scale, I think I can go to like 10 millivolts per division. 20, 10 millivolts per division, 10 millivolts per division. And I see no sign of my signal. So I guess you could say it must be smaller. I don't know. It's probably smaller even than 5 millivolts. So it's a 60. No, it's a 30 millivolt common mode signal, and I'd say it's even smaller than 3 millivolts output. Oh, right. Okay, so if we want to get a really decent measurement, let's go back over here and make this a little bigger. So let's make this, how about 1 volt? And I don't remember which one we're actually, no, we should be plugged into the first one. But okay, just for fun, we'll make them both 1 volt. Yeah. Okay, and we'll go over here, and we still see no sign of this input signal. Okay, so even 1 volt, and I'd say it looks like the signal is smaller than 10 millivolts, so it seems like it's smaller than 0.01. I guess we could even make the input signal a little bigger. Let's try 2 volts amplitude. And I don't think this one will do anything, but I'll change it to. Maybe we see a tiny little sign of it. Yeah, but anyway, so it seems like we're down in the 10 to the minus 2, 10 to the minus 3 range. I think we expect something like 10 to the minus 3 now for the differential gain, because I think we worked out that the effective R tail should be a couple of mega ohms. So that would be 10K over 10K over 4-ish mega ohms. Yeah, so I think we're down in the kind of 10 to the minus 3 range. Okay, and then here, let me just go back to using the 2 signals differentially, and you should see that the output is absolutely gigantic. See, it's so gigantic that these lines look vertical. And I guess we can change the voltage scale. So now we can go to, let's go to 2 volts per division. And we'll go to 2 volts per division. And okay, it seems like, see, now they're AC coupled, so it's hard to tell why, but it seems like they're saturating. Now I guess if we go to DC coupling instead of AC coupling on the scope inputs, then we can see that we're reaching a limit on the top because we reached the power supply, 9 volts. And then I think we're reaching a limit on the bottom because the transistor saturates. So now let's reduce the amplitude to let's do 50 and 50. That's a 100 millivolt differential signal. So here's 50 and 50. Okay, and we'll just, I like to just kind of, somewhat to be paranoid, I do stop all and run all just to make sure the synchronization is right between the channels. And okay, there we go. So we see, so that is a 0.1 millivolt differential signal, and the amplitude of the output, is, here, let's see, this looks like, we go up to here, and we go up to here, and then we can also move the trigger level up to something like 5 volts. Yeah, so I'd say it seems like the amplitude of that signal, let's see, 7.74 minus 2.37, and then divide by 2, is like 2.685. Okay, so I think that's a differential gain of something like 27. And again, I think because of these tiny, uh, because little RE is not negligible compared to the emitter resistors, this amplifier is sort of nonlinear, which means that I think that its gain is sort of amplitude dependent. So I think that's why you need to put in a very small signal to get the gain that we predicted with the straightforward equation. Then you can also see we have about a 5-volt offset, and I think that makes sense because you have 0.4 milliamps here. 0.4 milliamps times 10K is 4 volts. This would be 9 volts minus 4 volts is 5 volt quiescent V out. So indeed, you see a 5 volt quiescent V out, so that seems to make sense. Yeah, okay, so I wanted to revisit this and just show you that it appears that if we use the 3 transistors in this transistor array, there are 2 other transistors whose emitters are tied together, so that makes it hard for us to use emitter resistors. So if we use these 3 transistors in such a way that pin 13 is a very low voltage in the circuit. So initially it was just tied to -9, and then now it's just it's like a volt above -9. So anyway, it's lower than anything else going on in that transistor array. I think that gets rid of this problem that we saw, that the differential gain changed by like a factor of 2 when we connected this current source. So we found that the problem went away when we changed that. To be really rigorous about it, we should rewire it the other way and see if the problem comes back, and we should also like maybe make a circuit lab model that includes the diode effect that the manufacturer datasheet shows and see if that explains it. But for now, it seems like we have a pretty good hunch that the reason why I saw that mysterious drop in differential gain was that we were not using pin 13 according to the datasheet's recommendation. So I think we fixed that. So the write-up for lab16, if you do it on the EE board, should say use pins 12, 13, 14 for this current source, and use pins 6, 7, 8 for this right-hand half of the differential pair. Okay, that's good. On to the next lab.